Thank you very much, everybody, for sticking around to the last presentation of today. I'm representing Air University, Pakistan, and we have this joint project with Cambridge University. One of my I have collaborators from Cambridge CMOS Sensors, as well as Cambridge University, Professor Florin, Udrea. And within Pakistan, we collaborate Pakistan Institute of Engineering and Applied Sciences, as well as a team of my colleagues and students at Air University. Here is the outline of my talk. I'll first introduce the wall shear stress and the sensors which sense wall shear stress. And since my sensor is a thermal wall shear stress sensor, so I'll go over its measurement principle briefly, as well as the challenges. It will be followed by the sensor design, fabrication, packaging, and sensor characterization. Finally, I'll conclude my talk. The wall shear stress is the viscous force which acts on all the solid bodies when any liquid flows on top of them. And for Newtonian fluids, the viscous wall shear stress is given by this mathematical formula, which relates dynamic viscosity of the fluids with the velocity gradient at wall here. This is the place. More this velocity gradient, higher would be the skin friction drag or the shear stress. And more the dynamic viscosity of the fluid, this is a fluidic property. More would be the wall shear stress. Why wonder and why worry about wall shear stress? Wall shear stress is an important phenomena for all the aerial vehicles as well as submarines and ships. The aerodynamic shape which reduces the wall shear stress in the automotive is also one very important area. If you reduce the wall shear stress, just for an idea, for an aircraft flying, 50% of the friction which aircraft is overcoming is because of the skin friction drag. And in US in year 2000, there were about $10 billion worth fuel budget for all the airliners flying within the United States. And if you reduce it by 20%, you reduce the bill by $1 billion at least. So that's why people are worried about it. Even for the medical guys, the coronary artery diseases, the onset of the coronary artery diseases is linked to the wall shear stress at the endothelial cells, which when experience wall shear stress higher than the usual, there's a stronger chance of getting the heart attack. So computational fluid dynamics is a very important tool which can predict wall shear stress, but after all, experiments are the ultimate proof. So for any fluidic problems involving active flow control, turbulence models, in all these applications, CFD codes validation, and phenomena where flow transition as well as separation is important, wall shear stress is the key thing to be known to the scientist. There are a number of wall shear stress sensors available in the literature and in the market, but thermal ones have their own peculiar advantages, and I'll just cover the principle. It is very simple. You embed a hot film in line with the surface where skin friction drag is needed to be measured, and then you heat it electrically. The heat, as shown, is split into two parts. One goes back to the wall, one goes into the fluid, and the total is the flow, the power being inducted into the hot film. So if you relate the convected power to there's a calibration procedure through which you can relate the convected power to the wall shear stress, and this N is the unknown, which is to be calibrated for each different fluid, because every fluid has its own convection coefficient, and so on. So the requirements posed by thermal wall shear stress sensors are quite tedious. You need to be non-invasive, and hence the sensor has to be essentially flush mounted and causing no flow disturbances. The spectral resolution is of the order of 100 micrometers because of the size of the flow eddies, and the temporal resolution, you're sometimes interested in how fast the wall shear stress is fluctuating. So then the temporal resolution also needs to be catered, and it is a very small quantity. For example, a car traveling at 100 km per hour would experience only 1 Pascal of wall shear stress. So you're really looking at a very small quantity to be measured. And finally, you need to fabricate the sensor which are reliable, give you repeatable results, and are affordable at the same time. So CMOS is the solution to that. That's why this research focuses on CMOS wall shear stress sensors. Now I move to my sensor design, fabrication, and packaging. It's a very crude kind of animation, but we start with SOI wafers, and these SOI wafers have the device layer is removed, and it is rather replaced with the metal layers, which are actually used which is actually given in the CMOS process as interconnect layers. So we have 3 layers of metal, and we use them cleverly to create the sensors, the wall shear stress, the hot film sensors within, and finally we passivate to avoid oxidation of the films. And at end of the CMOS process, in a single post CMOS process, we get this cavity etch. It's deep rectified back etch air cavity. This is the cadence design of a sensor I would be presenting my results on. There's an array of sensor on this 4 by 4 millimeter chip, 50 micrometer, 100, 150, and 200 micrometer long thermal hot films in 250 micrometer membranes. And this is an actual fabricated chip. That was the cadence design, and here we have the actually fabricated. So all these membranes are silicon oxide membranes, back etched through a single deep rectified etching step. And the pads are then used to not only power the hot film, but also do the 4 probe measurements, because the sensors have very small resistance, and the resistance changes are very important for sensor functionality. This is a close-up of one of the sensors. We do have a sensor on the substrate as well, just to see how efficient we have been to recover the heat from running away by creating this membrane, silicon oxide membrane. So it's a tungsten hot film. This is a tungsten hot film and silicon oxide membrane created through deep rectified etching. And this is a sensor on tungsten hot film sensor on the substrate. Sorry for this typo. This is on the substrate, and this is on the membrane. And then we have 4 probe measurements to make sure that the resistance measurements are accurate. Now I come to the characterization results. Here's the TCR graph. The TCR we obtain is around 0.21% per degree C. Just for reference, polysilicon wall shear stress sensors were, a chain of them were produced by CM Ho and YC Ties group in Caltech and UCLA. They had a pretty low TCR. Another group at MIT and University of Florida, they reported platinum sensors with this TCR, and there's one odd CNT based wall shear sensor as well. So it's a pretty reasonable TCR. This is showing the efficacy of these membranes. There's a non-linear tilt in the IV curve because the heat is not running away. Heat is actually going into the fluid and not into the substrate. But for the sensor on substrate, it's almost pretty linear, showing that most of the heat is being absorbed back and very little is going into the fluid. Finally, using the TCR, we draw this temperature versus power graph and calculate the thermal resistance of the sensor and the membrane arrangement, and we get a very good thermal resistance, showing that the thermal isolation is pretty efficient. Moving on to the calibration of the sensor. This is a lucite plug in which we created a cavity and embedded the sensor chip, and sides were covered with UV adhesive to make sure there's a very plain, there's a very plain, smooth and plain airflow over the sensor chip. And these copper wires have, wire bondings to the sensor. And this plug comes in here, and these 4 wires are then connected to the constant temperature animatory circuitry. And this is the input given through these pipes to a microflow channel, and here is the exit. And through this calibration formula, we, against a known wall shear stress, we measure the pressure drop and hence create, against a known wall shear stress, we know the voltage change across the sensor using this CTA, traditional CTA circuit. So there is a sensitivity curve of the, as we heat the sensor more and more, overheat ratio 1 means that the sensor has double its original resistance achieved through joule heating. So maximum sensitivity is on overheat ratio 1, and its average calculated from 0 to 1.6 pascals is around 35 millivolts per pascal. And here is the comparison with some of the previous CMOS based wall shear stress sensors. For temporal resolution, we were able to achieve 16.7 kilohertz kind of frequency response, which is good enough. Beyond 10 kilohertz, anything beyond 10 kilohertz is good enough for most of the fluids. I come to the conclusion of my talk. We have presented a tungsten-based CMOS MEMS hot film wall shear stress sensor for the very first time and found it very viable and promising. The key thing here is silicon oxide membranes as opposed to silicon nitride membranes, mostly used in the past for these kind of sensors. Results are pretty good. We have achieved a good resolution, high TCR, ultra low power, and good time and frequency response, 40 microseconds and 16.7 kilohertz. And CMOS fabrication is the strength. It gives us lower cost, more reliable and repeatable performance, integration of on-chip electronics, and rapid redesigning and prototyping. That was all for today. Before that, I would like to acknowledge the funding provided for this project and for this travel to the conference by Higher Education Commission of Pakistan. British Council has provided the joint grant INSPIRE for working with the Cambridge group to continue this project, and the partial funding also came from Smart Silicon on Insulator Sensing System Operating High Temperature project funded by EU. Thank you very much, and I would be very pleased to take any questions.